Okay, so we are going to look at an example problem out of your textbook on two-object, one-dimensional motion. So this is example 2.112 in your textbook, and of course the book shows you one method, and I'm just going to give you that other strategy that we've been looking at. So it reads, Friday night football. Fred catches the football while standing directly on the goal line. He immediately starts running forward with an acceleration of 6 feet per second squared. And use that nasty empirical system, but because your book is using it, we'll just stick with it. At the moment the catch is made, Tommy is 20 yards away and heading directly towards Fred with a steady speed of 15 feet per second. If neither deviates from the straight ahead path, where will Tommy tackle Fred? All right, so we first want to identify what is the motion we care about. So what is our initial and what is our final? Now, the motion begins when Fred catches the ball. It's the same time Fred starts running and the same time Tommy starts running. So, the catch and the start of the run. I am not liking this thick pen. All right, and when does it end? Well, it ends at the tackle, so when they meet. Now, when we conceptualize the problem, switching pens on us, when we conceptualize the problem, we also want to think about what is related. Is it two objects? Is it one dimension? Is it multi-phase? And in this case, we have two objects, Fred and Tom. So we know we're dealing with a two-object problem. And whenever we deal with a two-object problem, we want to think about what's related. Well, they're going to meet, which means their final position of Tommy is going to equal the final position of Fred, and their time is the same. They're starting when the catch or the start of the run, and they're ending at the tackle. So the time of Tom is going to be equal to the time of Fred. So thinking about those relationships right off the bat is going to be really helpful in our problem solving. All right, now we have to identify the world and draw our picture. So here we have Tom. Tom's the catcher, right? Ooh, no, this is Fred. Here we have Fred. And let's say that Fred starts at x equal to 0. We'll define the origin at the location Fred catches the football. Oh, we need to have football in his hand. There it is. All right. Then, oh, excuse me. I'm back. All right. Tommy, it says, moves to the right. Well, Tommy starts at 60 feet and runs to the left. You know, 20 yards, he's 20 yards away, but he's starting at 60 feet. And since our 3 yards per feet, reverse that, 3 feet per yard. So since our acceleration is in feet per second, that's how we're going to be thinking of that. So here is Fred, or Tommy. He's going to be running this way. Fred was running this way. And since he's 20 yards away, he is 60 feet at x equals 60. So there's our picture, kind of representing the direction of each one's running. Okay, now we make our lists. So we have two objects, two lists. So here's Fred, x initial of Fred, x final, Fred, v initial for Fred, v final for Fred, acceleration for Fred, and time. All right, so when the catch is made, where is the position of Fred? He's right at 0. When, and we'll put 0 feet. When he ends, we don't know where he ends. His initial velocity, he starts running when the catch is made. So that means he is starting at 0 feet per second. Final velocity, we don't know. The acceleration is given, I've already forgotten what it was. 6 feet per second squared. And, time Fred, we don't know the time. All right, so there's our list for Fred. What about our list for Tom? All right, so we have the initial for Tom. We have the final for Tom. We have v initial for Tom, v final for Tom, acceleration for Tom, and time. All right, well, he starts at 60 feet. We said he was 20 yards away when the catch is made, 60 feet. We don't know where he ends. It says he's going at 15 feet per second. He's moving to the left. So that's negative 15 feet per second, as I've drawn it. We don't know his, well, it says he's moving at a constant, so we do know steady speed. We do know his final velocity is also 15 feet per second. The acceleration is 0, steady pace, but we don't know the time. All right, so here is our list for both players, both objects in the motion. Now, we want to know, where does the tackle happen? At what location? Well, that's my final position. So I want to know, where is Fred at the end? Where is Tom at the end? Either one's fine. I can go after either one. We always want to go after what we're interested in. So let's start with Tom. All right, well, if we think about our relationships, we have one for x final that has both acceleration and v initial in it. I'm just going to put that up here as the general. X final is equal to x initial plus v initial t plus 1/2 at squared. We might come back to that for Tom as well. So here we have Fred, x final. We don't know what it is. X final of Fred is equal to x initial, 0, plus v initial, 0, times time, I don't know, but it's going to be multiplied by 0, so that's not such a big deal, plus 1/2, 6, oh, there's that time of Fred squared. Well, I have another unknown in my relationship, but let's simplify it. Get rid of those zeros. These two things go away, and we end up with 3t of Tom, time of Tom, squared. Well, if I go back to my sources of equations, there is another one with time in it, but it's also missing v final. So I need to look somewhere else for time. But I'm going to remember that time is related to Fred. So if I knew Fred's time, I would know Tom's time. Reverse that. If I knew Tom's time, I would know Fred's time. And then I could use it. So our time becomes the next variable of interest. All right, well, I have the constant velocity relationship here. And because I am in a situation of constant velocity, that is the same relationship with this term gone. So we're going to utilize this relationship now for Tom. I have x final. Oh, I don't know what that is. X final for Tom is equal to x initial, 60, plus v initial, negative 15 times the time of Tom. So I can't solve for the time of Tom either to give me the time I need. But I'm going to remember this relationship. And so if x final of Fred equals 3 times the time of Fred squared, and x final of Tom equals 60 plus negative 15, the time of Tom, and these two relationships exist, then I'm ending up with two equations and two unknowns. So let's just rethink about those two equations. X final of Fred is equal to x final of Tom. Let's just call that x final, and then we'll be able to see these relationships. The time of Tom is equal to the time of Fred, so let's just call that time. So if I rewrite my equation, x final of Fred, we're going to call x final, is equal to 3. Time of Fred, we're just going to call t, 3t squared. And if I look at this relationship, I end up with x final of Tom, which we're just going to call x final, is equal to 60 minus 15 times the time of Tom, which we're just going to call t. Now I have two equations with the same two unknowns. And there's lots of different ways you can solve simultaneous equations. I personally like setting them equal to each other. So here I have x final, here I have x final. Let's set them equal to each other. So 3t squared equals 60 minus 15t. And I'm going to rearrange this so that it looks like a quadratic equation. I end up with 3t squared plus 15t minus 60 is going to equal 0. Now I have a quadratic equation, and I can solve for that quadratic equation using my quadratic formula. So the opposite of b, minus 15, plus or minus the square root of 15 squared, minus 4 times a, 3 times c, negative 60, all over 2 times a, 3. Now, this will give me two results. I have this plus and minus here. And according to your book, those two results are going to be, time is either going to equal negative 7.62 seconds or positive 2.62 seconds. Well, which one makes sense? Well, time, if our time is starting at time equal to 0 when the catch is made, then the time always has to be positive. So our time of this motion must be that positive time, because the other one's negative. Now be careful, we're not always going to get a negative time and a positive time, and it's going to be easy to pick. Sometimes we'll get two positive times, and we're going to have to think about what that means. But in this case, the positive time is the one that makes sense. So now that I have the time, I can use either one in my relationship. And I just think this one's a little easier. So we will start with x final equals 3 times 2.62 squared. And when I solve for that, I find that x final is equal to 20, I'm looking at your book again, 20.6 feet. Now, does that, or that's going to be yard. If we also want to think about it in yards, that's, divide that by 3, and we get about 6.9 yards. Does that answer make sense? Well, it's at a location of 20.6 feet, and that's between the two locations of the objects. So, it's not unreasonable. It's closer on this end. Well, that might make sense because, well, Fred, it's going to take him if we kind of logically think through this, in the first second, Fred's going to be going 6 feet per second. In the second second, Fred's going to be going 12 feet per second. Tommy's going 15 feet per second the whole time. So he's going to be able to cover more distance in those first 2 seconds than Fred is going to be able to. And so we might be biased towards Fred in terms of our position. So the relationship should make sense. That evaluation piece, think about, does this answer make sense? All right, good. So we want to think about these two object problems. This is the key. This idea of recognizing how they're similar and using that powerful relationship to solve for what we're interested in. All right, good job.